Polyol synthesis is a simple and versatile route, developed in 1989 by Fievet and Viau et al. To make colloidal particles of various shapes and sizes made of metals and their alloys. Polyol synthesis involves the reduction of an inorganic salt precursor by a polyol at an elevated temperature. Based on the synthesis method, nanoparticle synthesis is of two types: top-down and bottom-up process. Polyol synthesis is an example of bottom-up synthesis of nanomaterials. The first polyol synthesis article was titled Homogeneous and Heterogeneous Nucleations in the Polyol Process for the Preparation of Micron and Submicron Size Metal Particles. The present form of the polyol synthesis was developed by Sun and Wiley et al. They have made a number of modifications to the conventional protocol. Since then, tens of thousands of research articles on polyol synthesis have been published. Among these, silver nanowires have been the most intensively studied because of their unique physicochemical, optical, and mechanical properties, which far exceed those of their bulk counterparts. The traditional definition of silver nanowires is based on their characteristic size and shape. The diameter of a silver nanowire is typically 10 to 200 nanometers, and its length is generally 5 to 100 micrometers. In polyol synthesis of nanomaterials, polyol refers to alcohols containing multiple hydroxyl groups. Ethylene glycol, propylene glycol, pentane diols, glycerols, and so on are commonly used polyols. The polyols take advantage of several features, such as water-comparable solubility of simple metal salt precursors, (SANPRT), high boiling points, up to 320 degrees Celsius, RTD, reducing properties for the instantaneous synthesis of metals, IV, coordinating properties for surface functionalization and colloidal stabilization of nanoparticles, V, wide adaptability of the polyols ranging from low-weight ethylene glycol, EG, to high-weight polyethylene glycols, PEGs. Many precursor salts can easily dissolve in polyol. Apart from this, temperature-dependent reducing power and relatively high boiling points make polyols suitable solvents for making anisotropic nanoparticles. Upon heating in the presence of air, ethylene glycol converts into glycolaldehyde, which acts as a dominant reductant in the polyol syntheses of silver nanostructures. At elevated temperatures, ethylene glycol can reduce silver ions into silver atoms, and thereby induce the nucleation and growth of silver nanostructures in the solution phase. Many other reducing agents are used to reduce metal salts to generate nanoparticles using polyol protocol. Common reducing agents for nanoparticle synthesis include strong chemical agents like sodium borohydride and hydrazine, and weaker agents such as sodium citrate, ascorbic acid, vitamin C, and glucose. Other reducing agents include alcohols, amino acids, chitosan, and plant extracts or their compounds, which are often used in green synthesis. The choice of reducing agent influences the nanoparticle's size, shape, and stability, with strong reductants often yielding smaller particles. In high school or college chemistry experiments, Tollin's test is used to qualitatively distinguish between aldehydes and ketones. Tollin's reagent, ammoniacal silver nitrate, is added to an analyte. If it forms a silver mirror, then the organic compound has an aldehyde functional group. This is a positive confirmatory test for aldehyde and a negative confirmation of ketones. Similar chemistry is utilized in the polyol synthesis of silver nanomaterials. At elevated temperature, glycols form glycolaldehyde, which in turn reduces silver salt to generate elemental silver. In this redox reaction, silver ion, silver plus, get reduced to a metallic silver atom with zero charge, silver zero. Polyvinyl pyrrolidone is commonly used as a stabilizer or capping agent to prevent agglomeration of the colloidal particles in polyol synthesis. It has been demonstrated that this method is good for making nanostructures of silver, palladium, and platinum, as polyols have a relatively high dielectric constant and can serve as a good solvent for both metal precursors and PVP. Due to the presence of oxygen and nitrogen atoms in the pyrrolidone unit, PVP can adsorb onto the surface of silver and can stabilize the resulting structure. The extensive interaction strengths of PVP with different crystallographic facets of a silver lattice are different and could, therefore, induce anisotropic growth of silver. Capping agents exhibit a preferential affinity for the 100 facet of silver nanowires, promoting the selective attachment of silver atoms to the 111 facets. Multiple twinned seeds are decahedral in shape, with twin boundaries extending outward in a five-fold symmetry to include 10 111 facets. Silver atoms are attracted to the high-energy twin boundary surfaces through the Ostwald ripening process, selectively undergoing crystallization and elongation. Researchers believe the halide salt mediator serves two functions in the polyol reaction: scavenging oxygen and forming an Ag precipitate to prevent AgNP formation. During nucleation, silver precipitates are formed with halide salt mediator anions to release Ag+ slowly. During silver nanowire growth, the surfaces of the multiplied twinned Ag seeds are susceptible to oxygen adsorption. The halide-based salt mediator cation scavenges the oxygen and preserves the silver nanowire morphology. After silver nanowire synthesis, centrifugation and filtration methods are used for purification. These techniques remove undesired particles of different sizes and shapes. Ultrasonication can be used to break down nanowires and to remove aggregation. Ultraviolet visible UV-VIS spectroscopy is a crucial tool for characterizing silver nanowires, AGNWS, by analyzing their unique optical properties, which arise from surface plasmon resonance, SPR. The UV-VIS spectrum of silver nanowires reveals two distinct plasmon absorption peaks that provide information about their size, shape, and purity. The UV-VIS spectrum of silver nanowires typically shows two absorption peaks related to SPR, which is the collective oscillation of electrons on the surface of the silver nanostructure. Transverse plasmon resonance, around 350 to 380 nanometers. A sharp peak in the ultraviolet region corresponds to the resonance of electrons oscillating across the short axis diameter of the nanowire. Longitudinal plasmon resonance above 400 nanometers. A broader, weaker peak in the visible region, often appearing as a shoulder, is caused by the resonance of electrons oscillating along the long axis length of the nanowire. Applications. Silver nanowires have a wide range of applications due to their high conductivity, transparency, and heat transfer properties, including use in flexible electronics, transparent conductive electrodes, antimicrobial coatings, advanced sensors, high-performance catalysts, and specialized materials like aerogels for various industrial uses. Their one-dimensional structure gives them unique physicochemical properties that are leveraged to create new technologies for medicine, energy, and consumer products.